Swayam Prabha. Digital India. Educated India.
Giving a background on neural computation, that neural network based computation is very different kind of computation compared to symbolic AI, which relies on symbol manipulation on an infinite tape by a finite state head. So though the two systems are equivalent, as proved in 1967 or so by McCullough and Pitts, they're equivalent systems, but still, there is a matter of ease of expressing computation. Just like there are many programming languages which are all Turing complete. So they're all equivalent in the sense of being able to capture all computation. But we know that some languages are better for specific purposes. COBOL, for example, was business. Fortran is still the reigning programming language for scientific computation. Python is used for AI programming largely. So programming languages are used for specific purposes. Similarly, models of computation are used for specific purposes. So for pattern recognition, where you decide if the face belongs to a particular individual, or decide if a sentence has positive or negative emotion, or decide if a spoken signal depicts laughter or anger. So those kind of decisions are pattern recognition problems, and human beings are extremely good at them, whereas computers were pretty pathetic, and human beings are pretty pathetic. Okay, so human beings are pretty pathetic at numerical ability. Computers are at pattern recognition ability. So that's why this new, this alternate model of computation was proposed. So now discussing perceptron, we came to the point where we asked, can a perceptron, a single neuron, compute AND? And there we understood the problem was to find out W1, W2, the weights of the two connections and the threshold theta, so that for 0, 0, 0, 1, 1, 0, the output will be 0, and for 1, 1, the output will be 1. And for that, the condition is very clear. W1 into 0 plus W2 into 0 should be less than or equal to theta, because the weighted sum of the input, if it is less than or equal to theta, the threshold, then the output is 0. So we want W1 into 0 plus W2 into 0 to be less than or equal to theta. This means theta must be greater than or equal to 0. So then Y will be 0. Then W1 into 0 plus W2 into 1 must be again less than or equal to theta, because the output should be greater than, the output should be equal to 0. So that makes theta greater than or equal to W2. For 1, 0, x1 equal to 1 and x2 equal to 0, W1 into 1 plus W2 into 0 is less than or equal to theta. This implies W1 is less than or equal to theta. And finally, W1 into 1 plus W2 into 1 should be greater than theta. Then only the output will become 1. Then W1 plus W2 must be greater than theta. So we have these 4 inequalities. Should be non-negative, greater than or equal to 0. Theta should be greater than W2. Theta should be greater than W1 also. And but W1 plus W2 together should exceed theta. So theta should be greater than or equal to W1 and W2 individually, and theta should also be non-negative. And W1 plus W2 must exceed theta. So that condition can be satisfied by an infinite number of values for W1 and W2. Infinite number of values, right? So one of the possibilities is W1 and W2 both are 0.5 and theta equal to 0. Then no, theta should be equal to 0.9. Okay, so theta is 0.9. Then theta is greater than or equal to W2, greater than or equal to W1. But W1 plus W2 together exceeds theta. Okay, so so this is the value. If you fix on the perceptron W1, W2, and theta, then you can compute AND. So similarly, you can verify that you can compute OR, where for 0, 0, the output should be 0. And for any other combination, the output should be 1. So this way, we can compute many Boolean functions, but we cannot compute XOR. Okay. We cannot compute XOR. Let me see. Yeah. So this is the equation. These are the set of inequalities for XOR. So for 0, 0, output should be 0. For 1, 1, also output should be 0. But for 0, 1, and 1, 0, the output should be 1. So W1 into 0 plus W2 into 0 should be less than or equal to theta. That means theta should be greater than or equal to 0. And similarly, W1 into 1 plus W2 1 into 1 should be less than or equal to theta. That means W1 plus W2 should be less than or equal to theta. So theta is non-negative, and W1 plus W2 should be less than or equal to theta. Okay, but the fact that 1, 0 combination should make the output to be 1, that makes theta to be greater than W2, theta to be greater than W1. So you see theta is non-negative and theta is greater than both W1 and W2. How can theta be less than or equal to W1 and W2? So these 4 inequalities cannot be satisfied for XOR. So therefore we say that perceptron cannot compute XOR. Okay, so the perceptron can compute for 2 inputs all the 14 Boolean functions. From 2 inputs, you can get 16 Boolean functions. Out of them, 14 are computable by a perceptron. XOR and XNOR. XNOR is the equivalence function. The output is 1 if both the inputs are same. Otherwise, it is 0. Only XOR and XNOR cannot be computed out of those 16 Boolean functions. Okay, so out of 16 Boolean functions, 14 can be computed by a perceptron for 2 variables, and 2 cannot be computed. Now, there is this table. The functions that a perceptron can compute, they're called threshold functions. So if n is equal to 1, then 2 to the power 1 is 4. All these 4 functions can be computed by a perceptron. Okay, so the 4 functions, when there is only a single input, the 4 functions are equivalent. That means input and output are same. Inversion, for input as 1, output will be 0. For 0, it will be 1. Then for 0 and 1, the output will be same. These are called true function and false function. Okay, so there are 4 Boolean functions, and out of 4, all the 4 can be computed by a perceptron. Whereas out of 16 Boolean functions, for n equal to 2, 14 can be computed by a perceptron. Where if the number of inputs is 3, then out of 256 Boolean functions, 128 are threshold. When n equal to 4, out of 64k Boolean functions, only 1008 are threshold functions. So the number of functions out of the space of Boolean functions which can be computed by a perceptron falls very, very rapidly. Okay, so it can be shown. I know I have the proof of that, but may not have time to do it. That if n is the number of inputs, then the number of Boolean functions is 2 to the power 2 to the power n. But the number of threshold functions is 2 to the power order 2n square. Okay, order 2n square. So while the log of this number of functions, log of number of Boolean functions is exponential, the log of threshold functions is order n square. Okay, so this can be proved. This can be proved by what is called the capacity theory for the neural network. And this shows that the number of threshold functions is a very, very minuscule proportion of the possible number of Boolean functions. Okay, so we've already seen an example where the perceptron cannot compute important Boolean functions. So XOR is the parity function. XNOR is the equivalence functions. They appear all the time in real life examples. Okay, especially equivalence. You want to decide if two strings are equivalent or not. Was there a question?
Yes, sir. Is there a typo in the threshold functions number? Is it 2 power n 2n or 2 power n square?
No, this
in
is
the threshold functions.
Threshold functions. 2 power n square. N square. I'm sorry. This is n square.
Okay.
2 power n square. So the log of threshold functions increases in order n square, whereas log of number of Boolean functions is increases exponentially. So this should be n square. I'm sorry. So so this is an important discussion. Functions or functions computable is a starting point for neural network based computation. All neural computation starts from here, and the deep learning, of course, as you know, is an assembly of large number of neurons. So it is founded on computation by a single perceptron. So now the AND of two inputs gives me a particular set of inequalities, and I can find out W1, W2, and theta, a particular tuple W1, W2, and W theta. So, however, there are infinite number of values which can be satisfied by satisfied for these inequalities. Okay. So the discussion that we just now finished is an example of non-learning situation. Here we have all the inputs and outputs, and all that remains is to find out the W1, W2, and theta values, the weight and the threshold value. So that is not a learning situation, because the whole set of input and output pairs are given to the perceptron. In learning situation, we know only a part of the conceptual space is given, and the system should be able to generalize and come up with a description of the whole conceptual space, which has this generative capacity or predictive capacity. Okay, so that description of the conceptual space in future should be able to decide if the input and output pair is consistent, or if the input is given, what the output should be. Okay, just to make my comment grounded, the learning machine should be shown many examples of positive sentiment and negative sentiment sentences. From that, the learning machine should set its parameters such that when a new sentence comes, it can decide if that sentence is of positive sentiment or negative sentiment or neutral sentiment. So that is the characteristic of learning, right? Machine learning has this characteristic that a part of the conceptual space is shown, rest is not shown, rest should be obtained by prediction. So in perceptron training, now we look upon perceptron as a learning machine, okay? And therefore, all input-output pair is not given, or they are given incrementally, and there should be a way of fixing the parameters. In the inequality-based solution, the parameters were fixed at one go. Okay, we gave all the input-output pairs, set up the inequalities, and obtain the values of W1, W2, and theta by solving these inequalities. Now, the characteristic of learning situation is that the examples are given one by one, okay, and the parameter gets set for each example, which is called incremental learning. Of course, there is something called batch learning, but in incremental learning, this is what happens. And since this is again the most basic form of learning, let us understand how incremental learning can take place in perceptron. So we are discussing perceptron as a learning machine. So here what happens is that we are not very comfortable dealing with equality. So y is equal to 1 if sigma wi xi is greater than theta, and y is equal to 0 if sigma wi xi is less than theta. So we are getting rid of the equality test. Okay, only greater than test and less than test. Now, is this admissible? Can we do this? Yeah, we can. You can always show that a perceptron which has both greater than equal to theta test and less than theta test is equivalent to a perceptron which eliminates the equality test. So intuitively, the perceptron computes by drawing a hyperplane between the 0 class examples and the 1 class examples. All those input vectors which belong to 0 class, input vectors which belong to 1 class, the perceptron sets up a hyperplane between these two groups of points. Okay, so this W1, W2, and theta, there can be infinite number of values. So those W1, W2, theta values, if you put them on a hyperplane, put them in a three-dimensional space, it defines a hyperplane passing through the origin, and that separates the positive points from the negative points, or 0 class points from the 1 class points. Now, equal to means that some of the points fall on that hyperplane. Now you can give an infinitesimal shift to that hyperplane and make sure that none of the points are falling on the hyperplane, but still it is separating the positive class from the negative class. So then all you have is greater than test and less than test. Any point which falls on the 0 class has less than value. Any point which falls on the 1 class has greater than value. So so we can get rid of the equality test. So only positive and negative. Another thing we do is that we absorb theta, the threshold, as a weight. Okay. Now theta is the weight. We compare sigma wi xi with theta. Instead, I can take up theta on the left-hand side and subtract from sigma wi xi and compare with 0. So a perceptron where threshold is theta is equivalent to another perceptron where the threshold is 0. And there is a fictitious connection where the input is -1 and the weight of that connection is theta value and the threshold is equal to 0. Okay. So any perceptron where the threshold is non-zero can be converted to a perceptron where the threshold is 0 by introducing a fictitious connection where the input is fixed at -1 and the weight is theta. So what are the two things we have done? We have gotten rid of the equality test, only greater than and less than, and we have gotten rid of theta as threshold, but absorbed theta as a fictitious weight for the perceptron. Another thing we do is we can negate the 0 class. Okay, we can negate the 0 class. Then that will leave us with only one kind of test. That one kind of test will be greater than. Okay, so if I multiply all the 0 class vectors by -1, then all I have to test is greater than 0. So let me illustrate this. You are looking at OR perceptron. Can somebody verify this OR perceptron slide?
Yes, sir.
Yeah, okay. So in OR perceptron, we have the 1 class as 111001, the 0 class is 00. So since we have absorbed threshold also as a weight, we have to prepend, okay, or append in the front a fictitious weight of -1. So I append -1, -1, -1 to all the 4 vectors, and then I do not have to worry about threshold. I have to compare with 0. Okay, the weighted sum should be compared with 0. And I negate the 0 class. That means I multiply the 0 class components by -1. Then we have 1, 0, 0. Now, the 0 class vector should satisfy the test that their weighted sum should be less than 0. So if I multiply both sides by -1, then the less than test becomes greater than test. So all the vectors now have to satisfy on a single test which is greater than 0. All the vectors. So this pre-processing is very instructive. Now OR can be computed if I take these four vectors, minus 1, 1, 1, minus 1, 1, 0, minus 1, 0, 1, and 1, 0, 0, okay, zero class vector has been negated. So these four vectors, the three 1 class vectors and the negated 0 class vector, I now have to simply find a weight W, which is W0, W1, W2. That weight will multiply each of these vectors, and in each case, the weighted sum should be greater than 0. So my learning problem is now converted to finding a weight vector such that the weighted sum for each vector individually exceeds 0. That is all. Okay. So now we give a learning flavor to the whole problem, incremental flavor to the problem. So how do we get this weight?
Sir.
Yeah.
Could you again tell how could we discard the equality constraint part?
Equality. So equality, I have not given an equation. All I'm saying is that equality means that some of the points are falling on the separating hyperplane. Okay. So the separating hyperplane is essentially sigma wi xi equal to 0 is equal to theta. That is the equation of the hyperplane. Sigma wi xi equal to theta. Now equality means that though the points which satisfy equality test, they are falling on the hyperplane itself. So now we shift the hyperplane slightly by a very small amount so that none of the points are on the hyperplane, and the shifting has to be in the right direction. The points which are on the hyperplane, they should all move to the positive side. Okay, so you should move the hyperplane accordingly. Now there is a mathematical expression for this, which you can look up, or I can mention sometime. You have to give an epsilon movement to that hyperplane, and what that epsilon is depends on the values here. So that is what I said about removing the equality test. Okay.
Yes, sir. Thank you.
Okay, so we removed equality test, we removed the threshold or absorbed as a weight, and we also got rid of the less than 0 test by multiplying by -1. So now the OR vectors are -1, 0, 1, -1, 1, 0, -1, 1, 1, and 1, 0, 0. I have no worry about positive class, negative class. For all of them, the test should be greater than 0. Find a vector W which will multiply these and give you the value greater than 0. Now, the training algorithm is extremely simple and very elegant also. We start with some random value of W. Okay, so it's an iterative algorithm. Now I test if W.xi is greater than 0. If the test succeeds for I equal to 1 to n, that means for all the vectors, then we have found the required W and the algorithm stops. If not, then we modify the initial value by adding the failed vector itself. So the vector which did not succeed, I add it to the existing weight vector and then proceed with the same computation. So very, very simple algorithm and very elegant. All we have to do is to modify the weight vector by adding the vector which did not succeed the test. So, so this I have illustrated by this NAND example. In NAND example, what happens is for 0, 0, the output is 1. It is inversion of AND. So for 0, 1, output is 1, 1, 0 is 1, 1, 1, 0. So this is the NAND function. And I augment this with -1. And we also negate the 0 class. Then the 4 vectors that we have are 0, 0, -1, 0, 1, -1, 1, 0, -1, and -1, -1, 1. Okay. So x0 was augmented because threshold is absorbed as a weight. So -1, -1, -1 is added to all vectors. And this y is nothing but the class information. So when we negate the 0 class, I have to multiply the vector by -1 for each component. So -1, -1, 1. So now the 4 vectors I'm dealing with are 0, 0, -1, 0, 1, -1, 1, 0, -1, -1, -1, 1. Now I run the algorithm. I initialize and keep adding the failed vector. Initially W is 0, 0, 0. I start with the 0, 0, 0 vector. Thus, when I have 0, 0, 0, I find that the first vector 0, 0, -1 fails, V0 fails. So I add it and obtain W1, which is 0, 0, -1. With W1, I see that V3 fails, -1, -1, 1 fails. So I add it to obtain W2. So W2 is -1, -1, 0. Now V0 fails. I add V0, obtain W3, -1, -1, -1. With this new vector W3, V1 fails. I get W4 by adding V1 to W3. W5 I obtain by adding V3 to W4. W6 is obtained by adding V1 to W5. W7 is obtained by adding V0 to W6. V3 adds to W7 to get W8. V2 adds to W8 to give me W9. And now we begin to wonder whether the perceptron training algorithm will at all converge or not. Okay, we seem to be going on and on. Then W10 I obtain by adding V3 to W9. V1 adds to W11 to get W12. V3 adds to W12 to get W13. V1 and W13 gives me W14. Then I proceed. W15 I get by adding V3 to W14. V3 W15 gives me W16. V2 W16 gives me W17. V3 W17 gives me W18. Now when V1 and W18 are added, I get the right vector. -3, -2, -4. So W1 is -3, W2 is -3, W1 is -2, and W0, which is the threshold value, is -4. So now the algorithm is converged in 18 steps. So this is the famous perceptron training algorithm. It was given in 60s, and there is a very elegant convergence proof for perceptron training algorithm. But I suppose the training algorithm itself is clear to you. Every time you simply add the failed vector to the current weight vector, and you go on doing it, and finally find the weight vector. Now, this algorithm converges because of the following theorem. Whatever be the initial choice of the weights and whatever be the vector chosen for testing, perceptron training algorithm converges if the vectors are from a linearly separable function. That means if the function is computable by a perceptron, if it is computable by a perceptron, the perceptron will converge and give you the set of weights. That is the statement of the perceptron convergence theorem. And the amount of time it takes for the convergence to take place depends on the initial value and also the number of weights or the dimension of the input vector. As the dimension of the input vector increases, the number of input-output pairs also increases. Right. So the training data size and the initial value, if the initial value was exactly same as the final value, which separates the two classes, positive and negative, then without any computation, straight away in one go, you get the correct vector. So it depends on how you initialize. The best possible case is the initial weight found by random number generation happens to be the correct weight. Then you don't have to do any iteration. And if the initialization is such that it is far from the set of points which can separate the positive and negative class, if it is far from the hyperplane which separates the positive class from the negative class, then it will take many, many iterations. Okay. And it is also possible to show that instead of adding the whole vector, you can take a proportion of the vector. That means you can multiply each of the components of the vector by a constant between 0 and 1, and then add it to the weight vector. So that also will decide the speed of convergence. So that proportion which is added is called the learning rate. Okay, it's called the learning rate. So you can take this as an exercise. So if Satyam, if you're here, then put this as an exercise that in perceptron training algorithm, show that if not the failed vector, but a proportion of the failed vector is added to the weight vector, then also the separating weights will be found out. Okay, so don't add the vector, but a proportion of the vector, and that proportion is called the learning rate. Then also you will get the convergence. Now the convergence proof is very elegant. There are two proofs. One is the geometric proof, the other is a algebraic proof. So just for the sheer intellectual pleasure, let me give you the main steps of the proof. This proof was due to Marvin Minsky of MIT, and one of the most elegant proofs in AI. So are you looking at the slide called proof of convergence of PTA? Can somebody verify?
Yes, sir. Yes.
Okay. So what you're trying to prove is the perceptron convergence theorem. Suppose Wn is the weight vector at the nth step of the algorithm. Now, in the initial vector is W0. Now we go from Wi to Wi plus 1 whenever a vector xj fails the test, Wi dot xj is greater than 0. And we update the weight Wi as Wi plus 1 equal to Wi plus xj. So since xj is form a linearly separable function, that means you can compute that function. We can say that there exists a value W star, which can separate the positive class from the negative class. Or in other words, you can find a W star. There exists a W star such that this W star dot any of the vectors of the problem will give you greater than 0. Now we consider an expression GWN. GWN is formed from Wn dot W star divided by mod of Wn. Wn, you remember, is the weight at the nth iteration. And we are interested in showing the convergence of the perceptron training algorithm. So Wn is the weight at the nth iteration. Now GWN is equal to mod of Wn into mod of W star dot cos theta. This is the definition of the dot product divided by mod Wn, where theta is the angle between Wn and W star. So GWN therefore is mod of W star into cos theta. Wn cancels from numerator and denominator. Now the modulus of GWN should be bounded by modulus of W star, because cos theta is between -1 and +1. So we can see that whatever be the number of iteration, how many ever times the iteration continues, the magnitude of GWN is upper bounded. It cannot become infinity. So it is upper bounded by W star, which is a real valued quantity. W star is an actual vector. W star exists. So now we study the behavior of the numerator as n increases. So numerator is Wn dot W star, which can be written as Wn minus 1 plus xn minus 1 fail. Because at the n minus 1th iteration, there was a failed vector. We are calling that vector xn minus 1 fail. So I expand Wn as Wn plus minus 1 plus xn minus 1 fail. Now apply algebra, do some algebraic manipulation. Wn minus 1 dot Wn star plus W star into W star plus xn minus fail into W star. Now you see xn minus 1 failed dot W star must be greater than 0, because W star is the correct weight vector which separates positive class and negative class. And in particular, W star dot any vector must be greater than 0. So if that is the case, then I can say that this quantity can we can go on expanding. Okay, we can go on expanding, and we can see that this quantity becomes W0 dot W star ultimately plus X0 fail plus X1 fail plus X2 fail up to Xn minus 1 fail dot W star. So it becomes W0 dot W star plus summation of all the failed vectors into W star. Now, summation of any vector into W star must be a positive quantity. So this W0 dot W star, W0 dot W star is also a constant quantity, initial vector into W star, which is the separating vector. So this dot product is constant, and here you have n positive quantities. Okay, n positive quantities. So if the magnitude of any of the vectors is greater than or equal to delta, then this quantity must be greater than or equal to constant into n delta. So, this is a quantity which is n into some quantity, positive quantity delta plus constant. What is the behavior of the denominator? The denominator is magnitude of Wn, which is square root of Wn dot Wn. Now this is Wn minus 1 plus xn minus 1 failed to the power 2 square. Now apply a plus b square, Wn minus 1 square plus 2 Wn minus into xn minus 1 fail plus xn minus 1 fail square. Now Wn minus 1 into xn minus 1 fail must be less than 0. Must be less than or equal to 0. It is not greater than 0, which is why I went to the nth iteration. So then I have this quantity is less than or equal to Wn minus 1 square plus xn minus 1 fail square. So I can go on doing this n after n after n and come to a situation where I have the square of the initial vector plus x0 fail square plus x1 fail square up to xn minus 1 fail square, whole thing square rooted. So if I have the magnitude of xj to be less than or equal to some quantity rho, then I can see that the denominator is a function of square root of n, whereas the numerator was a function of n. Okay, so numerator was growing as n, and denominator grows as root n. So then what can we say? We can say that as n tends to infinity, GWN also should become infinite because numerator grows as n, denominator grows as root n. So the GWN quantity, this quantity, which we started with, this GWN must become unbounded. But GWN cannot be unbounded. Okay, it is bound by this fixed quantity W star. So then where is the contradiction? If n grows to infinity, goes to infinity, then GWN becomes unbounded. But GWN cannot be unbounded, so n cannot go to infinity. Okay, so that means n has to be bounded. That means the number of iterations must be finite. And number of iteration is finite means that the iteration should stop after some time. Okay, so that means the perceptron training algorithm must converge if the function is linearly separable. If the function can be computed by perceptron, the perceptron eventually will halt. The perceptron algorithm will eventually halt, giving you the correct set of weights. So this is a proof by contradiction, where we have shown that if the number of iterations becomes infinite, then there is a contradiction in the there is a contradiction which arises, and therefore n cannot become infinite. Okay, so this is proof by contradiction. So this is one of the most elegant proofs, one of the most elegant proofs in AI, and this is an algebraic proof for proof of convergence of perceptron training algorithm. There is a geometric proof also, so that you can look up on the internet or in some book on neural computation. Okay, so perceptron training algorithm, we wanted to spend some time because this is the starting point of the whole neural network-based computation, and the proof is really elegant. So So there is a problem which can come, which can be stated based on this property of the perceptron training algorithm. If a weight repeats while training the perceptron, then the function is not linearly separable. Okay, think about this point. When the perceptron training goes on, if ever you observe that a previously seen weight vector has appeared again, you can be sure that this training algorithm will never converge. Okay, that means the function you started with must be a not linearly separable function. Okay, so you should really implement the perceptron training algorithm and check that it does not converge for XOR, but it converges for AND, OR, etc. And you should also change the initial values to see what effect it has on the number of iterations. Okay, so this is not an assignment; it is a programming exercise for you. Okay, no, I'm not going to evaluate you on that exercise, but do please program the perceptron training algorithm, which is extremely simple, just maybe 10 lines of code. Okay, where you essentially perform the test of greater than 0 and add the vector to the weight if the test fails. That is all. But you should really code it and observe the behavior for both AND function, OR function, and XOR, XNOR function. So do for both linearly separable and non-linearly separable functions. So, so I guess now it is time for questions. So, are there any questions on the chat box?
Sir, there is one class-related question.
Yeah, okay.
Is the converse true? If the set of points is not linearly separable, then the weight will repeat at some step? Question mark.
No, converse is not known. No, converse is not known. It is not a necessary and sufficient condition. Okay, it is a sufficient condition. If ever you observe a weight repeating, the training algorithm will not converge. Yeah.
And one of the questions is related to the midsem as a doubt for question 1.
Yeah.
So the doubt regarding question 1 of midsem, if the stem of ladies is LADY and not LAD, shouldn't the stem of communicative be communicate with the E instead of communicate, and therefore the answer being 11?
Okay, so you see, there are 3 terms in linguistics called stem, lemma, and root. Stem, lemma, and root. Okay, so stem is the least canonical form. Okay? So stem is the least canonical form, whereas lemma is the valid dictionary word. So let me give you an example from Hindi. So I take the word ladka, and ladka gets transformed into ladke and ladkon. लड़कों ने खाना खाया, लड़के सो रहे हैं, लड़का जा रहा था. So the same word ladka gets transformed into ladke and ladkon. Now the longest canonical string from ladka, ladkon, and ladke is ladak. Okay, ladak. So this is called the stem, because this is the stem from which all the morphological forms get generated. But lemma is ladka, because ladak is not a valid language word. So linguistics definitely distinguishes between stem and lemma. Root has an ambivalent position. Sometimes root is looked upon as a valid language word. Sometimes it is looked upon as the longest canonical string. So, so linguists use these terms quite interchangeably and many times loosely. Now, in uncommunicativeness, communicat is the stem. So that string is there in Latin also. It came from Latin. So communicat is the valid stem, And then, of course, you can work out the other questions accordingly.
That's these are the two only questions.
Achha.
Sir, in that means the stem of ladies is lady. So ladies stem is
No,
not
no, no.
lad.
Stem of ladies is LAD.
Okay, sir. Yes.
Y comes there to give the valid lemma, and IES gives you the morphed plural form.
Okay. Yes.
Okay. So there are no more questions.
No, sir.
No more questions. So then maybe we can discuss some of the questions in the midsem.
Oh yeah, I think Akshay asked a question later. Yes, sir, you said G of Wn is the dot product, but isn't it the scalar projection of W star on W?
Yeah, that's right. Yes. So dot product gives you a projection, yes, of one of the vectors on the other vector. So let's take go to the end because parsing was covered before the midsem. Go to the end. So let's take this question. S goes to high. This is has the probability 1/3. S goes to S and S probability is 2/3. The probability has to add to 1 surely. Can you make it bigger? Screen.
Do you want the document with answers, all the parse trees, sir?
Yeah. That's what I want. The model answer.
Just give me a second to do that.
Yeah. So 9 and question number 8 and 9. Let's take 8 and 9. So S goes to high is 1/3. S goes to SS is 2/3. The probability has to add to 1. Now, this has a negative mark because I wanted you to show that you understand parsing. So the string given is high, and the number of parse trees is 5. So you can look at the parse trees. So parse tree number 1, S goes to S and S, and these S's are given numbers for the sake of convenience with discussion. So S2 goes to another SS, and then each of these S's produce high. So that is one structure which is coming from the 4 highs. So now the next parse tree is S1 goes to so S goes to S and S. And then I do not expand the left S. Okay, so I expand the right S, and that gives me SS. Now the left S gives you 2 SS, high and high, and then there is a new parse tree for this. Okay, so here what is happening is that the parse tree is, the first parse tree is balanced, there is no skew. Second parse tree is right skewed first of all, and then left skewed. The third parse tree is first right skewed, and then again right skewed. The fourth parse tree is first left skewed, and then again left skewed. The last parse tree is first left skewed, and then right skewed. So these are the 5 parse trees that you obtain, and therefore the correct answer is 5. And you need to be correct with the parse tree construction. So that is question number 8. Now question number 9. Here, what is the probability of the string high? So if I am given a context-free grammar, probabilistic context-free grammar, can I get the probability of a sentence in that grammar? So high is a sentence in that grammar. Now, those of you who are somewhat aware of language modeling and so on would know that the probability of a sentence is nothing but the language modeling probability. What is the probability of this sentence? Now, the probability of a sentence is equal to the sum of the probabilities of the parse trees. So that you can prove by Bayes' theorem. Probability of a sentence is equal to probability of sentence comma tree over all possible trees. This is called marginalization. You can always introduce a new random variable if you take the sum over all possible values of that random variable. So probability of S is equal to sigma probability of S comma T. T goes over all possible parse trees. So no, leave it there, Nitesh, leave it there. Now, probability of S comma T is probability of T into probability of S given T by Bayes theorem. Now, probability of S given T is equal to 1. So the probability of a sentence is equal to sum of the probability values of its parse trees. Okay, so that's a very nice lemma or theorem, you can say. So the same thing is being done. Now, since the sentence high has two parse trees, one right skewed, the other left skewed. So you construct the two parse trees and obtain the probability values of the two parse trees. Probability value of any parse tree is nothing but the multiplication of all the probability rules applied, all the rules applied. So when you apply S goes to SS, the probability is 2 by 3. When S goes to high, probability is 1 by 3. S goes to SS, 2 by 3. S goes to high, 1 by 3, 1 by 3. So you have to multiply 2 by 3 into 1 by 3 into 2 by 3 into 1 by 3 into 1 by 3. So this becomes 2 square by 3 to the power 5. Similar is the case with the other parse tree, which is left skewed, 2 square by 3 to the power 5. Now, if you add these two probability values, it is 2 into 2 square by 3 to the power 5. So 2 square into 2 is 2 cube. So here I wanted you to be very clear about the construction of parse tree first of all, then the fact that the probability of a sentence is equal to probability of its parse tree. That theory should be clear to you, and obtain the result. Here again, there is a negative mark because I wanted you to know these things. Okay, so that is it. First question now, which was asked right now. The most important concept here is the morphology tree of the word. So uncommunicativeness gets divided into uncommunicative and ness. Okay. Notice that you cannot break it as un and communicativeness. Okay, you cannot. You cannot break it through un and communicativeness because communicativeness is a noun, and un as a prefix gets attached to adjective. Okay, yes. So communicative is adjective, so you have to make it uncommunicative, and ness can get attached to an adjective to make it a noun. Now, uncommunicative will be divided into un and communicative. Communicative again has communicat and eve. So this is the morphology tree of the whole string. Now, the first question was, what is the length of the stem? The stem is communicat, which has 10 characters. So correct answer is 10. Next question is, what is the number of morphemes in the word? The number of morphemes is the number of leaves. So un, communicat, eve, and ness. So there are 4 morphemes. So answer is 4. And then the question number 3 is the tree is left skewed or right skewed. That means, is it left heavy or right heavy? So you can see that it is left skewed. There are more nodes on the left branch of the root than on the right branch. So it is a left skewed tree. And finally, what is the length of the tree, I think? Yeah. What is the maximum depth of the parse tree? So you start from the root and go to any of the 2 leaves, communicat and eve. So this length is 3. Okay. So here I have a negative mark because I wanted you to be clear about the parse tree and the nodes and the arcs between the nodes and the concept of path. Okay, let's go ahead. So this sentiment analysis question I have discussed already. Some of you have sent a mail asking for more discussion. I will have a Google Meet with you to discuss this further. Okay, now the question about right scanning and left scanning for part of speech tagging. The answer is that whether it is left scanning or right scanning, the answer will be equivalent. and you want a proof for this, I've given an informal statement, but the proof is in terms of see whether it is right scanning or left scanning, the likelihood part of the argmax computation. Okay, that is lexical probability, that will not change. Right scanning or left scanning will not affect that because it is probability of word given the tag at that position. What gets affected is the transition probability, probability of Ti given Ti minus 1. Now, probability of Ti given Ti minus 1 is count of Ti minus 1 Ti combination divided by count of Ti minus 1. Okay. Now, you can arrange the terms and see that this count of Ti minus 1 Ti, which is equal to count of Ti minus 1, it doesn't matter. The count is a commutative operation, right? It doesn't matter whether Ti comes first or Ti minus 1 comes first. The only problem is with the division. In one case, it will be count of Ti minus 1. In the other case, it will be count of Ti. So notice that count of Ti will come in the denominator for the next probability. Ti plus probability of Ti plus 1 given Ti. So what is so the denominators get adjusted and come out to be same whether it is left scanning or right scanning. So what I'll do is that in the next class, I will bring the count based expression and show that both the examples, both right and left scanning deal with the same expression. You can also yourself try it. Okay, break the probability values into counts.
Sir, but the count is in order, right? We are just not counting a bigram, we are counting like first one word occurs, then the other word occurs. So in the opposite direction, this is not symmetric, right? Because A followed by B count is not same as B followed by A count.
But A followed by B count is same as B preceded by A count, no?
Yeah.
So let me do it one thing. Let me open it up. You also just don't assume, intuitively. It is not intuitive, agree. That's why this question. You also expand all the probability expressions in count form, and count of A comma B is equal to count of B comma A. No, I mean if you keep preceding and following notion in mind.
But we were asked to use the same transition probabilities, right? In the assumption.
Yes. Yeah.
So it is possible that like A goes to B, if we have like a transition matrix, so A goes to B count is high, but B goes to A count is low. So when coming in the opposite direction, we will use the A goes to B, that is the opposite count, which is low. So the answer might come wrong.
Yeah. So possible, might, etc. Right? You do one thing. You sit down with the expression, huh? And look at it. I'll also bring the expression. Okay. So now I think the time is up. Thank you.